Hi everybody, welcome to ACE Engineering Academy. So these questions are from heat transfer and these are previous year questions before 2000 year, dear students. Now let us go for the first chapter, conduction here. So coming to the conduction chapter, the first question was asked in GATE 1990. See, this is 1 mark question. Thermal conductivity is lower for option A wood, option B air, option C water at 100 degrees centigrade, option D steam at 1 bar. See, we know that thermal conductivity of solids is greater than thermal conductivity of fluids. See, fluids can be liquids or gases and vapors as well. So now from this we can see thermal conductivity of wood will be more than that of water, and here air and steam are there. So steam at 1 bar is there, air is there. See, density and viscosity of steam is more than that of air. So therefore the thermal conductivity is lower for air. Option B is correct for this particular question here. Now let's go for the next question. So two insulating materials of thermal conductivity K and 2K are available for lagging a pipe carrying a hot fluid. So if the radial thickness of each material is same, so radial thickness of each material is same. Option A, material with higher thermal conductivity should be used for inner layer and one which with lower thermal conductivity for the outer. Option B, material with lower thermal conductivity should be used for inner layer and one with the higher thermal conductivity for the outer. Option C, it is immaterial in which sequence the insulating material are used. Option D, it is not possible to judge unless numerical values of dimensions are given. So let us see this question, dear students. Two insulating materials of thermal conductivity K and 2K. So let us draw. So these are around a pipe. Two insulating materials are there. So I am taking two diagrams here. So let us consider the inner radius as R, outer radius as 2R for this inner material, and this is 3R. And similarly here also this is R, 2R, and this one is 3R. Now in the first case I will put thermal conductivity K here and 2K in the outer material. So here I will put 2K and this one as K here. Now let us find out the heat transfer values. Okay, so heat transfer Q will be equal to overall temperature difference by sigma RTH. So this is the formula that we usually use. Now first of all, let us find the resistance of the first material, R1. So R1 will be ln 2R by R by 2 pi thermal conductivity, 2 pi KL. So this will be ln 2 by 2 pi KL. So this is the first resistance. R2 will be ln 3R by 2R divided by 2 pi, and here thermal conductivity is 2K multiplied by L. So this will be ln 1.5 by 2 into 2 pi KL. Now I can write this one delta T into 2 pi KL, this is common, divided by ln 2 plus ln 1.5 by 2. So let us put this as equation 1. So Q is equation 1. Now let us take the second case. In the second case, R1, thermal resistance R1 for the first material will be ln 2R by R by 2 pi into 2K into L. So for the first material we have used the thermal conductivity as 2K. So this will be ln 2 by 2 into 2 pi KL. Now R2, this will be ln 3R by 2R divided by 2 pi KL only, because the second material thermal conductivity is this one. So from this we can write ln 1.5 by 2 pi KL. Now let us write Q1 dash as the heat transfer of this one. So this one will be delta T into 2 pi KL divided by ln 2 by 2 plus ln 1.5. See, I have taken 2 pi KL to the numerator here. So that's why I am writing it like this. Now if you observe carefully, Q and Q1 dash both here, or Q and Q dash both here, see, Q is less than Q1 dash. So therefore, heat transferred in this one will be less than Q1 dash. So therefore, what we need to do is, the material with low thermal conductivity should be used for inner layer and one with higher thermal conductivity for the outer, because we are using it for lagging a pipe. So when we are using it for lagging a pipe, the material with lower thermal conductivity should be used for inner layer and one with higher thermal conductivity for the outer. So as we are considering these as insulating materials. Okay. Option B will be correct for this particular question. Now let's go for the next question. This question was asked in GAIN 96. For a given heat flow and for the same thickness, heat flow and thickness are same, the temperature drop across the material will be maximum for option A copper, option B steel, option C glass wool, option D refractory brick. So heat transfer Q is equal to delta T by L by Ka. So this is the formula here. Now from this, what we can write is heat transfer and thickness are same. So heat transfer and thickness are same means, so we can write like this, Ka into delta T by L. So heat transfer and thickness are same means delta T will be inversely proportional to the thermal conductivity. So temperature drop will be inversely proportional to the thermal conductivity. So therefore, first of all we need to check for which material thermal conductivity is more. So thermal conductivity will be more for copper. So thermal conductivity of copper is more than thermal conductivity of steel. This will be more than thermal conductivity of the refractory material. So refractory brick, and this will be greater than thermal conductivity of glass wool. So as the thermal conductivity of glass wool is the least, then the temperature drop across the material will be maximum for glass wool material. Okay. So because of this inversely proportional relation. Okay. Now let's see 2 marks questions here. So the first question was asked in GATE 91. So match the property with their units. Property: bulk modulus, thermal conductivity, heat transfer coefficient, heat flow rate. Units: watt per second, Newton per meter square, Newton per meter cube, watts, watt per meter Kelvin, watt per meter square Kelvin he has given. So bulk modulus, the unit of bulk modulus will be Newton per meter square. So this is the first one. Then thermal conductivity is watt per meter Kelvin. So thermal conductivity is watt per meter Kelvin, heat transfer coefficient watt per meter square Kelvin, and heat flow rate is in terms of watts. So this is the question, dear students, which was asked for 2 marks, which is very easy question. Now let's go for the next question here. For a current carrying wire of 20 mm diameter and thermal conductivity 0.5 watt per meter Kelvin, expose it to air 20 watt per meter square Kelvin, maximum heat dissipation occurs when thickness of insulation is option A 30 mm, option B 25 mm, option C 20 mm, option D 15 mm. So this question was asked in GATE 93, dear students. So wire is given, we can assume this as a cylinder. So diameter is 20 mm, outer diameter is 20 mm. Thermal conductivity of the insulating material wire is 0.5 watt per meter Kelvin, H is 20 watt per meter square Kelvin. So we need to find the thickness of insulation. So we need to find thickness of insulation For that, first of all, we need to find the outer radius. Outer radius will be 10 mm here, dear students. Then critical radius for cylinder, this one will be K insulated by H naught. So K insulated value is 0.5, H naught value is 20. So this will be 0.025 meters. So which will be equal to 25 mm. Now the critical thickness of insulation TC will be critical radius of insulation minus outer radius. So critical radius is 25 mm minus 10. So this one will be 15 mm. So the maximum heat dissipation occurs when the thickness is 15 mm, dear students. Option D is correct for this particular question. Now let's go for the next question. GATE 96, 2 marks question. For a current carrying wire of 20 mm diameter having thermal conductivity 0.5 watt per meter Kelvin is exposed to air which is at 20 watt per meter square Kelvin. Maximum heat dissipation occurs when thickness of insulation is. Same question, dear students, but the year is different: 30 mm, 25 mm, 20 mm, 15 mm. So we need to find the thickness of insulation TC. So for that, outer radius is 10 mm here. Critical radius is K insulated by H naught. This is wire. So we can consider it as a cylinder. So 0.5 by 20. This one will be 0.025 meters, which is equal to 25 mm. So thickness of insulation TC will be RC minus R naught. So RC is 25 minus R naught is 10 mm. So 15 mm is the answer for this particular question. Option D is correct for this particular question here. Okay. Now let's this question. This question was asked in GATE 98, dear students. The temperature variation under steady state heat conduction across a composite slab of two materials with thermal conductivities K1 and K2 is shown in the figure. Then which of the following statements are correct? So option A, K1 is greater than K2, option B, K1 equal to K2, option C, K1 is equal to 0, option D, K1 less than K2. So K1, K2 are the thermal conductivities. Let us consider the thicknesses as L1 and L2 here. So temperature drops are there, T1 minus T3 and T3 minus T2, two temperature drops are there. So which of the following statements hold good? So he said steady state heat conduction. So therefore heat transfer in the first portion must be equal to heat transfer in the second portion. Now, so we need to identify which condition is correct out of these. So for that, let us solve this by using a small technique, dear students. So let us take the first temperature drop in the first slab as delta T1 and in the second one as delta T2. And here I am taking the angle as alpha and here the angle as beta. So thickness of this first one is L1 and the second one is L2 here. So therefore, let me write like this: tan alpha is equal to opposite side by adjacent side. So L1 by delta T1. Then tan beta will be L2 by delta T2. So under steady state condition, we know that heat transferred in the first slab will be equal to heat transferred in the second slab. So Q is equal to K1A into delta T1 by L1. So this will be equal to K2 into area into delta T2 by L2. So this is what is the condition. So from this, what we can write is K1 by L1 by delta T1 is equal to K2 by L2 by delta T2. L1 by delta T1 is alpha. So from this, K1 by tan alpha, this will be equal to K2 by tan beta. Now if you observe this diagram carefully, angle alpha is more than beta. Angle alpha is more than beta. So therefore, tan alpha by tan beta, if we write, tan alpha by tan beta will be equal to K1 by K2 So alpha is greater than beta. That implies tan alpha will be greater than tan beta. Now, if you observe carefully, alpha is greater than beta, tan alpha is greater than tan beta. So, from this, we can write K1 is greater than K2. K1 is greater than K2 here. So, therefore, option A will be correct for this particular question here. K1 is greater than K2. So, by using simple geometry, we have done this, dear students. Now, let's go for the next question. This was asked in GATE 99. So, it is proposed to coat a 1 mm diameter wire. So, outer diameter is 1 mm, dear students, and wire we can consider it as a cylinder with enamel paint. So, insulation of enamel paint is 0.1 watt per meter Kelvin to increase heat transfer with air. Air side heat transfer coefficient H0 is 100 watt per meter square Kelvin. Insulated material thermal conductivity is 0.1 watt per meter Kelvin. The optimum thickness of enamel paint should be option A 0.25 mm, option B 0.5 mm, option C 1 mm, option D 2 mm. So here, in order to increase heat transfer with air, we need to find out the optimum thickness or the critical thickness, because at critical thickness only the heat transfer will increase and it will reach the maximum point. So therefore, what we need to do is, we need to take outer radius first. So this one will be 0.5 mm. Then critical radius RC will be K insulated by H0. K insulated is 0.1 by H0 is 100. So this one will be 0.001 meters, which is equal to 1 mm. Now the critical thickness of insulation TC will be RC minus R0. So 1 minus 0.5, which is equal to 0.5 mm. So option B will be correct for this particular question. Now let's see the questions on fins and transient heat conduction. So 1 mark questions. The first question is asked in GATE 89, dear students. The heat transfer process between a body and its ambient is governed by an internal conductive resistance ICR and an external convective resistance ECR. The body can be considered to be a lumped heat capacity system if option A ICR is greater than ECR, option B ICR is marginally smaller than ECR, option C ICR is equal to ECR, option D ICR is negligible. See, ICR stands for internal conductive resistance and ECR stands for external convective resistance. See, in order to consider lumped heat capacity system, Biot number should be less than 0.1. So Biot number will be given as internal conductive resistance by external convective resistance. See, if internal conductive resistance is negligible, then only we can get the Biot number less than 0.1. So therefore, this value should be very negligible compared to ECR. So therefore, option D will be correct for this particular question. Okay. Now let's go for the next question. This was asked in GATE 91. Biot number signifies option A, the ratio of heat conducted to heat convected. Option B, the ratio of heat convected to heat conducted. Option C, the ratio of external convective resistance to internal conductive resistance. Option D, the ratio of internal conductive resistance to external convective resistance. Option D will be correct, dear students, because Biot number is internal conductive resistance by external convective resistance. So option D is correct for this particular question. Okay, now let's see this question. This question was asked in GATE 94. So when the fluid velocity is doubled, the thermal time constant of the thermometer used for measuring the fluid temperature reduces by a factor of 2. So this is what he is asking. So true or false question, dear students. Fluid velocity is doubled, then what happens to the thermal time constant? So for that, let us use this relation T minus T infinity by T naught minus T infinity is equal to e power minus tau by tau star. So tau star is the thermal time constant here. Okay, so we know that thermal time constant tau star will be equal to rho Vc by Ha. So from this we can write tau star is inversely proportional to the heat transfer coefficient. So therefore we can write like this: tau 2 star by tau 1 star is equal to H1 by H2. So this is what we can write. Now for laminar flow, if we consider, Nusselt number is directly proportional to Reynolds number to the power 0.5. So Nusselt number is HLC by K. So H will be directly proportional to Reynolds number. Reynolds number value is rho Vd by mu. So density is a constant. With respect to velocity, we are considering diameter or length of the plate will be constant. Then mu is also a constant. So therefore H is directly proportional to V power 0.5 we can write. Then for turbulent flow, if you consider, Nusselt number is directly proportional to Reynolds number to the power 0.8. So from this H is directly proportional to V power 0.8. Now let us consider for laminar flow tau 2 star by tau 1 star. For laminar flow, so this will be H1 by H2, which is equal to V1 by V2 whole to the power 0.5. So V1 is V by V2 is 2V, twice the velocity it is increasing to the power 0.5. So 1 by 2 to the power 0.5. So tau 2 star will not be equal to or reduces by the factor of 2 tau 1 star. So in laminar flow this is not possible. Let us see the turbulent flow case also. So in turbulent flow case, if you consider, in turbulent flow also here H is directly proportional to V power 0.8. So therefore if you substitute for turbulent flow also, here you can write tau 2 star by tau 1 star is equal to V by 2V whole to the power 0.8 you will get. So this also will not satisfy this condition. So therefore this statement is false, dear students. So this statement is false. So here we are using the thermal time constant formula and we are considering both the flows, laminar and turbulent flow, and we are identifying whether the given statement is true or false. Okay. Now let's see this question. This question was asked for 2 marks in GATE 92, dear students. Two rods, one of length L and the other of length 2L, are made of the same material and have the same diameter. Both are made of same material and same diameter. The two ends of the longer rod are maintained at 100 degrees centigrade. One end of the shorter rod is at 100 degrees centigrade and the other end is insulated. Both the rods are exposed to same environment at 40 degrees centigrade. So T infinity is 40 degrees centigrade. The temperature at the insulated end of the shorter rod is measured to be 55 degrees centigrade. So this is for the shorter rod. Temperature at the insulated end. The temperature at the midpoint of the longer rod would be, so option A 40 degrees centigrade, option B 50 degrees centigrade, option C 55 degrees centigrade, option D 100 degrees centigrade. Now let us draw this shorter rod and longer rod here. So let us consider this is a short rod which has a one end at 100 degrees centigrade and the other end is insulated. Okay, ambient temperature T infinity is given as 40 degrees centigrade and temperature at the insulated end is measured to be 55 degrees centigrade. That is what he has given. So temperature at the base TB is equal to T naught is equal to 100 degrees centigrade. This is for the shorter rod. Okay. Now let us take the longer rod. One end of the longer rod is at 100 degrees centigrade and the other end is also at 100 degrees centigrade. And the most important thing that you need to understand is the shorter rod length is L here, whereas the longer rod has a length of 2L. Ambient temperature is both for same, so 40 degrees centigrade. Now, so here what we need to do is, these are of same material and have same diameter, that is what he is giving. So we need to find out the temperature at the midpoint of this longer rod. So at x is equal to L, we need to find the temperature. So for that, what we can do is, we can use the formula theta is equal to theta 1 into sin h of m into 2L minus x plus theta 2 into sin h of mx divided by sin h of 2ml. This is the formula that we can use here. Okay. So let us see how we can use this formula and how we can get the temperature at that particular point. So before that, let us solve this particular condition. So here one end of the fin is insulated, one end of the tip is insulated. So T minus T infinity by T naught minus T infinity is equal to 1 by cos h of ml. This is the formula that we can use here. So T value is 55 minus T naught value is, or T infinity value is 40 by T naught value is 100 minus 40. So this will be 1 by cos h of ml. Okay. So 15 by 60, this is equal to 1 by cos h of ml. That is what we need to get here. So from this we will get cos h of ml value is equal to 4. So 15 ones, 15 fours, this will get strike off. So therefore cos hml is equal to 4. This is what is the equation which you have to remember now. Now we need to find out what is theta 1 and theta 2 and then substitute the value of x is equal to L, because we need to find out the temperature at this point T. Okay. So theta will be T minus T infinity, that we will write theta 1. So theta 1 will be this side temperature 100 minus ambient temperature 40. So this will be equal to 60. Theta 2 this side 100 minus 40, again this is also equal to 60. So let us substitute it here, 60 sin h of m into 2L minus x, 2L minus, instead of x we need to substitute L here, plus theta 2 is 60 sin h of mx. So sin h of ml we are writing here, divided by sin h of 2ml. So we can write this as 2 sin h of ml cos h of ml. So this is the formula we can write here. Now this one will be equal to T minus T infinity. So T infinity value we know it is 40 degrees centigrade. Now let us solve this one. So 60 sin h of ml, this will be plus 60 sin h of ml. 60 sin h of ml plus 60 sin h of ml will be 120 sin h of ml divided by 2 sin h of ml cos h of ml. Now sin h of ml gets cancelled. This will be 60 by cos h ml, 60 by cos h ml. So as both rods are of same material and of same diameter, So cos HML value will be same for both the rods. So therefore, we can substitute 4 value here. So this will be equal to 60 by 4, which is equal to 15. So from this, T is equal to 40 plus 15, which is equal to 55 degrees centigrade. So by using this method, we have got answer as 55 degrees centigrade. See, another method is also there to solve this particular problem, dear students. So this is a little lengthier method. We have used the correct formulas and we have got the value. See, if you observe, if I overlap this small rod over this one, so then what is going to happen here? So this insulated tip temperature will fall exactly at this particular point. So that means here also there will be some temperature. So therefore what will happen, that temperature will be same as this temperature because both are made of same material and both are having same diameter. Is it clear, dear students? So option C will be correct for this particular question here. Now let's see the questions on convection. So 1 mark question, the first question was asked in gate 88. For the fluid flowing over a flat plate with Prandtl number greater than unity, the thermal boundary layer for laminar forced convection, option A is thinner than the hydrodynamic boundary layer, option B has thickness equal to 0, option C is of same thickness as hydrodynamic boundary layer, option D is thicker than the hydrodynamic boundary layer. See, in the question it is given that Prandtl number is greater than unity. See, when Prandtl number is greater than unity, then the hydrodynamic boundary layer thickness will be greater than thermal boundary layer thickness, because we know that for a flat plate, hydrodynamic boundary layer thickness by thermal boundary layer thickness is equal to Prandtl number to the power 1 by 3. So by using this relation, if Prandtl number is greater than 1, then obviously hydrodynamic boundary layer thickness will be thicker than the thermal boundary layer thickness. In the question he said the thermal boundary layer for laminar forced convection will be thinner than the hydrodynamic boundary layer. So option A will be correct for this particular question. Okay. Now let's go for the next question. This question was asked in gate 90, dear students. So in pool boiling, the highest heat transfer coefficient occurs in option A subcooled boiling zone, option B nucleate boiling zone, option C partial film boiling zone, option D film boiling zone. See, the correct answer for this question, the highest heat transfer coefficient will be there when there is highest heat flux. So that happens usually during the nucleate boiling zone. So let us see the diagram here. You can observe here. See, the bubble formation will be majorly in the nucleate boiling zone where the agitation of the bubbles will increase, and as a result of the increase of this agitation of the bubbles, so there will be an increase in the heat flux, which in turn causes the amount of heat transfer coefficient to be higher. So therefore, in the nucleate boiling region, so you will be having more heat transfer coefficient, whereas in the other zones, the heat transfer coefficient will be comparatively less. So you can see this diagram. So here this will be representing heat flux on y-axis, x-axis, the excess temperature difference that we are considering. So nucleate boiling zone will be here, dear students, where heat flux is increasing. So as a result of this, the heat transfer coefficient also will increase. Okay. Now coming to the next question, this question was asked in gate 94, dear students, for 1 mark. For air near atmospheric condition flowing over a flat plate, the laminar thermal boundary layer is thicker than the hydrodynamic boundary layer. So true or false he is asking. So in this question he said air near atmospheric condition. So when air is near atmospheric condition, Prandtl number will be equal to 1. So over a flat plate, the laminar thermal boundary layer is thicker than hydrodynamic boundary layer. This statement is false, dear students, because for air near atmospheric condition, Prandtl number is equal to 1. So that implies hydrodynamic boundary layer thickness will be equal to thermal boundary layer thickness. Okay. So this is the answer for this particular question. Now coming to the next question. heat transfer coefficients for free convection in gases, forced convection in gases and vapors, and for boiling water lie respectively in the range of. So this question you have to remember the heat transfer coefficients of various things. So here he has given option A 5 to 15, 20 to 200 and 3000 to 50,000 watt per meter square Kelvin. Option B 20 to 50, 200 to 500 and 50,000 to 1 lakh watt per meter square Kelvin. Option C 50 to 100, 500 to 1000 and this one is 1 lakh to 10 lakhs he has given. Then option D 20 to 100, sorry option D 20 to 100, 200 to 1000 and a constant 10 lakhs watt per meter square Kelvin. So here the correct answer for this particular question will be option A. See, free convection in gases. So for free convection in gases, usually the range will be between 5 to 25, dear students, and for forced convection in gases and vapors 25 to 250, this will be the range. And for boiling water, so for boiling water this will be around 5000 to 10 power 5 watt per meter square Kelvin. So the nearest answer for this one will be option A, so we can consider this. Okay, now let's go for the next question. These are 2 marks questions. The first question was asked in gate 92, dear students. So a fluid flowing over a flat plate has the following properties. So dynamic viscosity is given. So dynamic viscosity mu is given 25 into 10 power minus 6 kg per meter second. So usually the units will be Newton second per meter square. So Newton second per meter square or kg per meter second, both are same. Okay, then specific heat 2 kilojoule per kg Kelvin, convert this into joule per kg Kelvin. So 2000 joule per kg Kelvin. So thermal conductivity is 0.05 watt per meter Kelvin. K value is given. So specific heat is given, viscosity is given, thermal conductivity is given. The hydrodynamic boundary layer thickness is measured to be 0.5 mm. So delta H value is also given 0.5 mm. The thickness of the thermal boundary layer would be, so we need to find the thickness of the thermal boundary layer. So for that, first of all we need to find Prandtl number. So for Prandtl number will be mu Cp by K. Mu value is 25 into 10 power minus 6 into 2000 divided by thermal conductivity is 0.05. Upon calculation, you will get Prandtl number is equal to 1. So when Prandtl number is equal to 1, hydrodynamic boundary layer thickness will be equal to thermal boundary layer thickness. In the question, hydrodynamic boundary layer thickness is given as 0.5 mm. So therefore, option B will be correct for this particular question here. Okay. Now let's go for the next question. So here the match the following type of question is given, which was asked in gate 96, dear students. Match list 1 with list 2 and select the correct answer using the code given below the lists. Okay. So list 1, he has given the dimensionless numbers, Grashof number, Schmidt number, Weber number, Fourier number. In list 2, he has given mass diffusion, transient heat conduction, free convection, forced convection, surface tension and radiation. See, here he didn't give any options, just we need to match accordingly. So Grashof number plays a very significant role in natural convection or free convection. So therefore, for Grashof number, free convection we need to consider. Then Schmidt number. So Schmidt number is usually used in mass diffusion. So therefore, mass diffusion will be correct for this particular Schmidt number option. Then Weber number. So Weber number is for surface tension. So this is correct. Then Fourier number. Fourier number is for transient heat conduction. So Fourier number is for transient heat conduction. Now I'll write the correct options. A 3. So Grashof number, natural convection. Schmidt number mass diffusion. So B1. Then Weber number is for surface tension, C5. And then Fourier number is for transient heat conduction D2. Okay, so this is the correct answer for this particular question. Now let us see the questions on radiation. So the first question was asked in GATE 88, dear students. So for a glass plate, transmissivity and reflectivity are specified as 0.86 and 0.08 respectively. The absorptivity of the glass plate is, see, transmissivity tau is given here and reflectivity rho is given. So we need to find absorptivity alpha. So for that 4 options are given, 0.86, 0.08, 1 and 0.06 as the options. See, we know that the sum of absorptivity plus reflectivity plus transmissivity. So this is equal to 1. So absorptivity is not known to us. Reflectivity is 0.08 plus transmissivity is 0.86. This is equal to 1. So from this, alpha will be equal to 1 minus 0.94, the sum of these two. So this will be 0.06. So option D will be correct for this particular question. Now let's see the next question. A diffuse radiation surface has option A, radiation intensity independent of angle, option B, emissive power independent of angle, option C, emissive power independent of wavelength, option D, radiation intensity independent of both angle and wavelength. See, he is saying diffuse radiation surface. See, we'll have two types of reflection. So one is specular or regular reflection. Suppose if you consider a body like this, see the intensity of radiation falling on this body, let us say this is the intensity of radiation G falling on the body. Now the reflected radiation is like this, GR. Now if we draw a vertical axis here, now if the angle made by the intensity of radiation with the normal drawn to this surface is equal to the angle made by the reflected radiation normal to this surface, then we call this as specular or regular reflection. But in the question he is asking diffuse radiation surface related thing. So therefore, so if we take a diffuse radiation surface, then if the intensity of radiation falling on the object is like this, the reflected radiation will not make the same angle with the normal drawn to the surface as the intensity of radiation falling. So therefore, the diffuse radiation intensity will be independent of the angle. So that's why option A will be correct for this particular question. And if you observe, we didn't discuss anything about the wavelength here. Okay, so radiation intensity will not be considered with respect to wavelength in this particular case. So diffuse radiation surface has radiation intensity independent of angle. So this is diffuse radiation, dear students. Okay, now let's go for the next question here. The question is asked like this. The shape factors with themselves of two infinitely long black body concentric cylinders with a diameter ratio of 3 are dash for the inner and dash for the outer. So concentric cylinders, he said. So let me take the cross section of these cylinders. So this is 1 and this is 2. Now the ratio of the diameters is given. So ratio of diameters is given as 3. So if you observe carefully, outer diameter is more than the inner diameter. So, d2 by d1 value we need to take it as 3. d2 by d1 is 3. Now, surface area of the first one is pi d1 into L. For the second cylinder, pi d2 L. These are the surface areas. Now, we need to determine the shape factors. See, when there are two surfaces, then the number of shape factors will be 4. For example, if there are n surfaces, the number of shape factors will be n square. Okay. Then, so here 4 shape factors will be there. The 4 shape factors are F11, F12, F21 and F22. See, the fraction of heat leaving the first surface will not strike it again. So, therefore, the shape factor with respect to itself of the first surface is 0. F11 is 0. Then, to find F12, we need to use summation rule. So, if we use summation rule here, F11 plus F12 is equal to 1. So, from this F12 is equal to 1 we are going to get, because F11 is 0. Then, we need to find F21, F22 as well. So, for that we will be using reciprocity theorem first. So, reciprocity theorem will say like this: A1 F122 is equal to A2 F221. So, from this F21 will be equal to A1 by A2 into F12. So, A1 is pi D1L and A2 is pi D2L into F12. So, F12 value is 1. So, from this we will get D1 by D2. So, F21 value will be 1 by 3, because D2 by D1 is 3 here. So, D1 by D2 will be 1 by 3. Now, again using summation rule, for the second surface, F21 plus F22 is equal to 1. So, from this F22 is equal to 1 minus F21. So, 1 minus D1 by D2, which is 1 minus 1 by 3, which is equal to 2 by 3. Okay. So, F11 is equal to 0. This is the first thing which we have to consider. So, F11 for the inner, this is 0, and for the outer F22 we got 2 by 3. So, 2 by 3 is the answer for this particular question. Okay. Now, let us go for the next question. This is 2 marks question which was asked in GATE 93, dear students. So, the radiative heat transfer rate per unit area. So, we need to find out the radiative heat transfer rate Q between two plane parallel grey surfaces of emissivity 0.9 maintained at 400 Kelvin and 300 Kelvin. So, first surface is at 400 Kelvin, second surface is at 300 Kelvin. Stephen-Boltzmann constant value is given sigma B. So, we need to find out heat transfer. So, as these are parallel grey surfaces, this is having emissivity epsilon 1, emissivity epsilon 2. So, both are same. So, emissivity epsilon 1 is 0.9 and epsilon 2 is also 0.9. Okay. So, the temperature of the first surface is 400 Kelvin, temperature of the second surface is 300 Kelvin. So, we need to find out the heat transfer. Q is equal to sigma B into T1 power 4 minus T2 power 4 by 1 by epsilon 1 plus 1 by epsilon 2 minus 1. Now, sigma B value is given as 5.67 into 10 raised to the power minus 8 into T1 value is 400 Kelvin. So, 400 to the power 4 minus 300 to the power 4. See, remember one thing, dear students, always you need to consider temperatures in terms of Kelvin in case of radiation heat transfer. Okay. So, divided by 1 by 0.9 plus 1 by 0.9 minus 1. So this will be approximately equal to 812 watt per meter square. So option B will be correct for this particular question. Okay, these are the questions from radiation. Now let's see questions on heat exchangers. The first question goes like this. In a shell and tube heat exchanger, baffles are mainly used to option A, increase the mixing of fluid, option B, increase the heat transfer area, option C, deflect the flow in desired direction, option D, reduce fouling of tube surface. This question was asked in GATE 91 for 1 mark, dear students. See, in shell and tube heat exchanger, baffles are mainly used. Baffles are mainly used in order to create turbulence, and at the same time, that will be helping in changing the direction of flow also. So we can deflect the flow in desired direction when these baffles are present in the shell and tube heat exchanger. Not only that, it will help us in supporting the tube also. So therefore, option A and C will be correct for this particular question. Okay. Now let us go for the next question here. This question was asked in 94, dear students. The practice to use steam on the shell side and water on the tube side in condensers of steam power plant is because option A, to increase overall heat transfer coefficient, water side velocity can be increased if water is on the tube side. Option B, condenser can act as a storage unit for condensed steam. Option C, rate of condensation of steam is invariably smaller than the mass flow rate of cooling water. Option D, it is easier to maintain vacuum on the shell side than on the tube side. See, he said steam on the shell side and water on the tube side. Why it is commonly used? See, if steam is not used on the shell side and if steam is present in the tube side, then one vacuum pump is not sufficient in order to maintain the required vacuum. So therefore, what we need to do is the steam should be maintained on shell side and water on the tube side so that we can use one vacuum pump in order to maintain the desired vacuum. So option D will be correct for this particular question. It is easier to maintain vacuum on the shell side than on the tube side because only one pump will be sufficient here. So if we keep the tube side, so we can't maintain the vacuum. So one pump will not be sufficient to maintain the vacuum. So therefore, we need to keep shell side, the steam and water on the tube side. Okay. Now let's go for the next question here. So this question was asked for 2 marks in the year 97 here. So in certain heat exchanger, both the fluids have identical mass flow rate specific heat product. The hot fluid enters at 76 degrees centigrade. So hot fluid inlet temperature is 76 degrees centigrade and leaves at 47 degrees centigrade. Hot fluid exit temperature is 47 degrees centigrade. And the cold fluid is entering at 28 degrees centigrade and leaves at 55 degrees centigrade. So cold fluid inlet temperature and cold fluid exit temperature are given. The effectiveness of the heat exchanger is. So in the question he said identical mass flow rate specific heat product. So that means mass of hot fluid, specific heat of hot fluid will be equal to mass of cold fluid, specific heat of cold fluid. So that means heat capacity of the hot fluid is equal to heat capacity of the cold fluid. So this is the given thing here. We need to find the effectiveness. So usually this type of thing happens in case of counterflow heat exchanger. So let us draw the diagram of counterflow heat exchanger, temperature versus length of the heat exchanger here. So this one TH1, TC2. So this is TH2, here it is TC1 here. Okay. Now in order to find effectiveness of the heat exchanger, the formula to determine effectiveness is actual heat transfer to the maximum possible heat transfer. See, actual heat transfer can be heat lost by hot fluid, capital CH into TH1 minus TH2. Okay, or we can write it as capital CC into TC2 minus TC1. This is heat gained by the cold fluid. So both of these will be correct for the actual heat transfer. Then coming to the maximum possible heat transfer will be minimum heat capacity multiplied by hot fluid inlet temperature minus cold fluid inlet temperature. See, if you observe carefully, the maximum possible temperature difference will be between hot fluid inlet and cold fluid inlet. So therefore, in order to have maximum heat transfer, so we need to consider maximum temperature difference multiplied by minimum heat capacity. Heat capacity is nothing but heat absorption capacity of the fluid. So if heat absorption capacity is higher, then heat transfer rate will be less. So heat absorption capacity should be less, then we will have more heat transfer. So that is the reason we are taking C minimum here. So C minimum into TH1 minus TC1. So heat capacities are same. So these will get striked off. Now we will determine the effectiveness. TH1 is 76 minus TH2 is 47 divided by TH1 is 76 minus, so TC1 is 28. So upon calculation of this one, you will get the answer as 0.604. So effectiveness is 0.604 here. Now let us see here, TC2 is 55 minus TC1 is 28 divided by 76 minus 28. So this will be approximately 0.56 something you are going to get. But in the options, both are not there. So options are given 0.16, 0.58, 0.721. So both are not there. So we can take the mean of these two. So that means on an average the answer will be 0.58. So option B will be correct for this particular question. Okay. So we need to consider 0.58 as the answer. Now let's go for the next question. Air enters the counterflow heat exchanger. In the question itself, he mentioned counterflow heat exchanger at 70 degrees centigrade and leaves at 40 degrees centigrade. So air is the hot fluid here. Then water enters at 30 degrees centigrade and leaves at 50 degrees centigrade. So cold fluid temperatures are given here. The LMTD in degree centigrade is, so options are given as 5.65, 14.43, 19.52, 20.17. This question was asked in GATE 2000. Now counterflow heat exchanger is given. Let us take temperature versus length graph here. So this is cold fluid inlet temperature, cold fluid exit temperature, hot fluid inlet temperature, hot fluid exit temperature, because in the question he has given counterflow heat exchanger. Now we need to calculate theta 1 and theta 2 values. So theta 1 is TH1 minus TC2. So TH1 value is 70, TC2 is 50. 70 minus 50. This will be equal to 20 degrees centigrade. Then theta 2 is TH2 minus TC1. So TH2 value is 40 minus TC1 is 30. So this will be 10 degrees centigrade. Now LMTD theta m formula will be theta 1 minus theta 2 by ln theta 1 by theta 2. So theta 1 value here is 20 minus 10 by ln 20 by 10. So you will get the answer as 14.43 degrees centigrade. So option B will be correct for this particular question. Now remember one thing, dear students, if theta 1 is 20 and theta 2 is 10, the value of LMTD should lie in between 20 and 10 only. So therefore these two options by seeing you can eliminate. Okay. So answer lies in between these two, right? So you can use the relevant formula and get the answer for this particular question. Okay.